Hey, welcome to this video on structs, traits, and implementations. My name is Doug Milford from Lambda Valley. Structs, or structures, are similar to classes or objects in other languages, with some notable distinctions. Structs represent complex data types that you as the developer define. For those of you coming from an object-oriented world, structs are object-oriented in some respects, but not in others, making them object-oriented-ish. They don't quite fit the true definition. We'll explore how they're similar but different. For one, there's no inheritance in Rust, but it can have methods. I'll also discuss traits, which is how Rust performs certain abstract behavior similar to what polymorphism does in object-oriented languages. But since there's no inheritance in Rust, it's not quite the same. And lastly, we'll discuss how you can use Derive traits using macros. There's a lot to get through, so let's get started. At first, this may feel very similar to other languages. A struct is defined by the struct keyword. Give it the name you want in Pascal case, meaning the first character is capitalized, as well as the start of any words, and then all other letters are lowercase. The body of the struct is defined by curly brackets, and inside we can define the fields we want of the struct, or in other words, the data elements. I'm going to give this 3 fields: an int, a float, and a bool. The field names should be snake case, meaning all lowercase where words are separated by underscore. The names can be whatever you like, and hopefully it's descriptive enough for other users to know what they represent. I'm just giving these dummy field names for demonstration purposes. We're going to get a warning. I'm going to annotate the struct with allow dead code to get rid of those. I don't recommend you do that in production, but for this demo, I don't want to be distracted by yellow squigglies. Notice with Rust that the field definitions end with a comma. Other languages often end field definitions with a semicolon, but not Rust. Also notice that the last field also has a comma. Some languages don't allow this. However, one of the most important things in programming is consistency, and I recommend every line have a comma. The reason being is if you added a field later, your source control won't have to highlight 2 lines instead of 1. It's just easier on the eyes in my opinion. But if you don't like it, Rust will compile just fine without a comma on the last line. Data structures can get pretty hairy with hundreds of fields. In my career, I have experimented with multiple ways of organizing fields, sometimes by importance, sometimes by use, sometimes by type. But usually the easiest way ends up being simple alphabetical. That's not a requirement, but it's something I try to stick to, so I'm going to put these in alphabetical order. If you're organized in the beginning, it saves you time in the end. If you noticed, because I have a comma after every line, I didn't need to mess with adding or removing commas as I refactored. Anyways, so now that I've defined what Doug's data looks like, let's go ahead and create a variable. We use the let keyword just like we do with primitives, give the variable a snake case name, and just set it to Doug's data and give it the data needed for each field. Okay, let's see what happens if you forget to include one of the fields when we're creating a new struct. The compiler will help you out and tell you what's missing. Awesome, my friend! Thanks, compiler! So let's try to update a field on Doug's var. That seems quite natural to do in most languages, right? Uh-oh, we get a compile error. If you remember from the data primitives video, variables are immutable by default, meaning they can't change. If we want to modify a variable, aka mutate it, we need to put mut in front of it. And now everything is grand! Notice that I didn't need to tell each field it's mutable or not. I tell the variable, and then all fields follow those instructions. I'm going to show you a different way to initialize data using existing data. I'll create a new variable, specify the fields I want, and use the dot notation on an existing variable to fill out the rest of the fields. What this is saying is that I have some int that I want to set to 200, but for all other fields, use Doug's var as values. You can manually set as many fields as you like and then use the ... notation at the bottom. This comes in handy on occasion. In more complex scenarios down the road, we may have to worry about ownership and stuff, but we'll wait until we reach that topic in a future video. I'm going to get a little more complex on you now. I'm going to create a new file that will contain a different data structure to demonstrate some things about visibility. I'm going to call it random info. I'll just give it two simple fields similar to what we have in Doug's data. Back in the main file, I can import the new file by typing mod random_info. I'll also use a use statement so that when we're referencing structs and other things from the other file, I don't have to constantly keep typing the mod name. That may not make sense right now, but we'll be discussing this further when we talk about code organization. Because our random info struct is in a different file, it's going to affect the visibility of our structure. I'll show you what I mean. If I create a new variable of type random info, IntelliSense should be able to see that type and give me the option when I type R. But it doesn't see it. The reason being is anything in the same file can see your struct like we saw with Doug's data. But with random info being in a different file, we have to say it's public to other files by putting the pub in front of it. And now we can see the struct random info in our IntelliSense. I'll go ahead and give the field some values like we did before and a compiler. Because random info is in a different file, the visibility of the fields themselves is also more strict. We have to tell them explicitly which fields are public. Rust will assume everything is private unless specified otherwise. That goes for both structs as well as its fields. This gives you some control over who can see what data. So let's change our structs such that all fields are visible to the outside world. And now our compile errors and warnings go away. Brilliant! There are very valid reasons for having private fields, and I'm not advocating that your fields should be private or public. But in this specific case, I want them all available to the other files. For those of you coming from an object-oriented world, you might be tempted to use random info as a base class to inherit from because Doug's data has some exact same fields plus more. But Rust doesn't support inheritance. You may think that's a good or a bad thing, but the Rust team had their reasons for doing it. Instead, Rust embraces composition over inheritance. If I wanted to reuse a struct in all of its functionality, I can compose it like so. There's hot debate on whether inheritance or composition is better, and it's a bit of a philosophical discussion. I'm firmly in the composition side. In Rust, there's no way to inherit, so it's kind of a moot point. We now get a compile error on Doug's data initialization because it doesn't initialize the random field. One way to do it is to define it directly in our initialize like so. If that suits your purposes, that's perfectly valid. But let's see a couple more ways to do this. This is a nice segue into how to do methods similar to object-oriented programming as well as introducing traits. Although Rust shuns inheritance, Rust does support other object-oriented concepts, although in a fashion you may not be used to. In most other object-oriented languages, you can add methods to the body of the struct like this. In Rust, you actually do it outside of the struct definition. This can feel goofy-footed to a lot of people at first, but it's easy to get used to. The water's warm. As a side note, we're doing what's called associated functions because they're associated with a struct type. You use the impl keyword, meaning implement or implementation, followed by the type you're implementing for. Inside of that area is where you put your functions and methods. I'm going to create a function to generate a new variable. I'll make it public so that other files can see it. I'm going to call it new by convention, but if you need to call it something else, there's nothing stopping you. I can use any number of parameters I need. It could mirror the field structure or not. It depends on if you're doing calculations to initialize your data or even hard coding. I'll just have one parameter to at least have something. I need to return something from our function, so I'll return random info since that's what we're creating. Now, that'll work just fine, but the convention of an implementation block is to use the self keyword. The compiler knows that self is the random info type that you're implementing for. It helps keep things abstract, and if you see it in someone else's code, you should know what it means. Capitalization is important, and self represents the type, so the first letter is capitalized. Now you can code to your heart's content to prep any data needed to create your return variable. This is just like any other function. I don't have a need for heavy calculations for this guy, so I'm just going to return a new random info variable immediately. Again, I'm going to utilize the self keyword. The compiler knows you mean random info because we're inside of that implementation block. As a reminder, the way a function knows what to return is when you omit your semicolon. Here, I'll use the opposite of param a with the not operator of the exclamation point to initialize my sum bool just to perform some type of transform on our parameter. And I'll also hardcode a sum int to 8. Again, this is just dummy data for demonstration purposes. We're getting a warning because new isn't used anywhere yet, which we'll do shortly. Self. I know this is odd at first, and we're about to see another use of self. The notation threw me for a loop the first time I saw it, but all it means is I'm returning a type of self, which the compiler knows this is random info, and then returning the initialized struct of self. Again, the compiler knows it's random info. Now, back in the main file, I can use the new function with the double colons. Let's add another function that will use actual data in the random info struct. I'm going to create a new function called isSmaller. To be able to use data from our struct like object-oriented programs would, we would make the first parameter self. Haha, I warned you it was coming. In this case, it's all lowercase with an ampersand in front of it. This is different than the capitalized self. Capitalized means it's a type. Lowercase means it represents actual data. This is how you can access and modify the data of your struct internally. I'm going to add another parameter, and it'll be the caller's responsibility to provide that. I'll just return back whether the data on the struct for sum int is smaller than the passed in parameter. The comparison provides a boolean, so we'll just need to return that straight back by not putting a semicolon at the end. And back in our main file, let's use it. Notice that the self parameter is assumed because we're using it on a data variable. You as the developer need to provide the rest of the parameters, and you're off to the races. So notice we have two ways we're calling a function implemented on the type. One is with the dot operator, and one is with two colons, and it might be confusing why. The difference is if you're going to be reading or writing to a variable using the lowercase self keyword, that will make it a dot operator. If you don't have the lowercase self keyword in the params, that indicates it should be a function available to the type itself accessed by the two colons. So far we haven't done internal updates on our data known as mutations. Let's say I want to keep a count of how often a function is called. I'll add a field called callCount, and I'll chase down all the compile errors. You know, some people hate compile errors. I think they're awesome. They prevent so many bugs, particularly during refactoring. I almost feel like I'm cheating using it. You know exactly what's wrong and where. Okay, now it compiles. Great! So now let's try to update some data in our isSmaller function. We get a compile error because Rust assumes immutability by default. To fix this, we need to tell the compiler that self is mutable with the mut keyword after the ampersand. Now that compiles, I can see we have another compile error in the main. Let's go ahead and check that out. This says that we're mutating something, but I don't have the variable defined as mutable. To fix that, I put an MUT in front of that variable name, and now it works. This chasing down errors and warnings is considered to be a nuisance by many people learning Rust for the first time. It's the opposite of the loosey-goosey JavaScript. The compiler can be somewhat annoying at first because all you want to do is A, B, and C. But Rust is ensuring you can do A through Z. In the end, the strictness saves you time because errors and debugging time plummet, which is really where projects get bogged down. Anyways, I'm sidetracking. One valid question is, why is the implementation of function and methods outside of the struct definition? One reason, and perhaps there's more, is it makes it easy to augment someone else's struct. In object-oriented programming, you might inherit from a base class and then add more functionality. With Rust, you can just implement anywhere you like. So, in the main file, let's do a different implementation for a function called isLarger. And now I can use it just like I would any other function or method on the struct, even though it wasn't defined in the struct definition. So it doesn't matter if you're using somebody else's struct buried in some referenced crate. You can extend it quite easily. Object-oriented programming also has a concept of polymorphism, meaning treating different objects the same regardless of whether they're inherited or the base type. Rust handles polymorphism a little differently with something called traits. In the random info file, I'm going to create a trait called SumTrait. It begins with the trait keyword followed by the Pascal casing of your trait's name. And of course, it'll be public so that other files can see it. Here we can define what should be implemented if a struct wants to utilize SumTrait. I'll create a function definition called isValid. It's just like if we're implementing a function on a struct, except that we don't actually write the body, we just put a semicolon after the type. Note that the reason Rust uses self as an abstract keyword might make a little more sense now. Since a trait can be applied on an indefinite number of structs, it wouldn't be feasible or perhaps possible for us to create a distinct function signature for each one. But with the self keyword, it doesn't matter. It's a way for us to be more abstract about our programming. In line with that, let's say you wanted to implement a function that compared a different variable of the same type. I can create a signature like this. Let's hold off on that one for now, as I think we're jumping a little too far ahead. Okay, so we're back to having a single function definition on our trait. Let's use that on our random info struct. We start with impl. Put our trait that we're implementing, for, and then the struct you're implementing for. We get a compile error because we haven't implemented the isValid function from our trait yet. So let's go ahead and do that. I'm just going to return back some bool as our result. When implementing a trait, you don't need to put whether it's public or not. It's just implied to be public. In fact, it'll give you a compile error if you put pub in front of the function name. No worries if you forget and put pub in there. The compiler will tell you why it's complaining. Let's go ahead and use our newly fulfilled trait in the main file on our variable. The dot operator now shows isValid as one of our available functions. You may be wondering what the trait even bought us. It was so similar to how we define other functions, so what's the point? Well, a trait pretty much decouples function definitions so that it can be used on multiple structs. This is how Rust achieves polymorphism. Let's give you an example. I'm also going to implement the trait on Doug's data. I'm just going to return back true because, hey, it's Doug's data, it's always valid, right? And now I can create a function that can accept multiple types. I'll create a function called printIfIsValid that accepts a trait, not a struct. The ampersand means I'm borrowing, which is a topic we haven't covered yet. Soon enough, one step at a time. For traits as function parameters, you'll need to use the dyn keyword. I'm going to delete some code so that we can see everything on one screen, so I'll also be cleaning up the errors and warnings as I go. If you didn't notice, the compiler was able to quickly identify all issues that could go wrong immediately as I was removing things. I'm telling you, the compiler is your best friend. The only warning we have left is on our new function, and that's because we haven't used it yet. So let's do so. I can call the function on any data type that implements some trait. Since both of the random info struct and Doug's data implement our trait, we can call the function for each. We now have two completely data types being passed to the same exact function, thus implementing our Rust version of polymorphism. Rust has some predefined traits that you might want to use as well. One is called default, so let's do that for Doug's data. The default trait just has a single function called default, and its return type is self. Let's create some data to be returned as the default, and that's all there is to it. Now, if you ever need a default, you can do it like this. As a reminder, if you don't see the lowercase self in your function parameters, you would access this with the double colon from the type definition. If you do see it, it's accessed through the dot operator on a variable. I don't see self on our default parameters, so we use the two colons in this situation. You can start to get pretty abstract with traits, and some traits have helpers in the form of macros. One that you've seen throughout these videos is the debug trait, which is often used when printing to the terminal or a formatted string. You get a compile error because we aren't implementing the trait debug yet. Instead of you implementing the trait by hand, which would be tedious, someone has created a wonderful macro to implement that trait for us. We just annotate the struct with derive debug. The compiler complains because Doug's data also has a reference to random info, so it too will need to implement the debug trait. And now everything compiles. Rust is super tight in making sure things compile recursively. It would have been really easy to forget that Doug's data had a field of random info. The compiler makes sure you don't shoot yourself in the foot. Derived traits from macros are a little magical and auto-generate a lot of code for you instead of forcing you to do it by hand. Macros are a wonderful part of Rust and is an advanced topic. You can do some extremely powerful things. There are other predefined traits that we can implement via a macro. You can implement copy or clone, or even such things as equivalence, partial order, yada yada yada. This is just a short list of what's possible. If I hover my mouse over one of these guys, it will give you a description about what it does. I encourage you to explore. There are just a few more brief topics I want to touch upon before we call it a day. A struct doesn't need to have any fields and is called a unit struct. The reason you might want to do this is if you want to group some functionality together even if there's no data. I haven't had much use for this, but you might. Traits can be implemented for unit structs just like you would do any other struct. There's also generic structs. I don't want to get too deep into this as we'll be diving into generics deeper in a future video. With these, you can define a single struct that can work across multiple types. If you're familiar with generics, this should make sense. If not, don't worry about it until you get to the generics video, and we'll go more in depth. Generics is a very useful topic in my point of view and worthy of your attention. And lastly, you can create a struct that is more like a tuple. You reference the fields with a zero-based index just like you would with a tuple. The difference is this has a type name and a tuple doesn't. Again, I haven't had much use for this one, but you might. I'm getting these warnings because they're not being used anywhere. Since we're at the end of this video, I'm not going to bother. Well kids, that wraps it up for structs, traits, and implementations. I hope you enjoyed this video. Once again, my name is Doug Milford from Lambda Valley, and I'll see you next time.